Hi everyone, today we will continue with the chapter Limits and Continuity. Alright, so today's chapter will be mainly on evaluating limits using L'Hopital's rule and also table. What I mean by table is the common exponential and logarithmic limits that we discussed in the last lesson. Alright, so today's lesson will involve a lot of L'Hopital's rule and we have to differentiate a lot of functions including transcendental function. So if you are new to calculus and this limits and continuity is your first chapter, I would recommend you to come back after you have learned differentiation and also transcendental functions. Alright, so without wasting any time, we will start now with the exercises. So today we have 15 exercises from your worksheet 2.6. Okay, so let's look at the first question. Okay, so because this is not approach infinity, so you can't actually use the the shortcut, right? You comparing the degree on top, degree at the bottom, then it is either 0, infinity, or constant. Because in this case, the limiting the limit, the c is -3. So you have no choice but to check whether you can direct substitute. Seems like -3 square is 9, 9 minus 3. No, you can't do that, isn't it? So what is your next approach? So if you have a look at it, it is actually 0/0 if you put in -3, isn't it? So now you have the, okay, let me write like this. Okay, 0/0. So now you have the passport to use L'Hopital's rule. Okay, remember to use L'Hopital's rule. Okay, to use L'Hopital's rule, just in case you forget, we need either 0/0 or infinity/infinity. Then other indeterminate form cannot. You need to make it into a quotient, which is the 0/0 or infinity/infinity. Okay, so now we can just go ahead and do a L'Hopital's rule. Now right here, by L'Hopital's rule, alright, by L'Hopital's rule, we just go ahead and differentiate the top, which is 3x squared minus 4 and 2x minus 1. Okay, now can you substitute in your -3? You can, isn't it? So it will be 3 -3 square minus 4, 2 -3, then minus 1. You will not get anything crazy. So it will just be, this is 9, 3 times 9, 27 minus 4, so it's 23 on top. At the bottom you have -6 minus 1, which is -7. Okay, so the answer will be -23/7. Okay, so this is a very simple L'Hopital's rule problem, because sometimes you need to use L'Hopital, you need to differentiate for multiple times until you get rid of 0/0 or infinity/infinity. Right, let's move on to the second question. Okay, so one look at it, you see theta approach 0 and you have all the trigonometric limits. Okay, so your first guess should be, maybe you need to make use of sine theta over theta, isn't it? The limit as theta approach 0, sine is equals to 1. Maybe you need to make use of this. So to make use of this, you need two things, which is, number one, you need sine, and number two, you need the angle. Maybe it's either one of them is on top, another one is at the bottom. So seems like in this case, we already have our we already have theta square here, which we can separate into 2. So I think we are good to try this. Okay, so in order to do that, we know that we need sine. So we'll just go ahead and make everything in terms of sine and cos. Okay, so tangent would be sine over cos. Okay, I will write the theta square here. Cotangent 1 over cotangent is actually tangent. Okay, so it will be sine 3 theta cos 3 theta. Okay, so I will go ahead and distribute this to this fella here and also to this fella here. Hence, I will have the limit as theta approach 0, sine theta over theta. Okay, this one is done. Sine 3 theta over theta. We know that we need a 3 theta, right? So just write like this. And what's left? 1 over cos theta cos 3 theta, right? Then just go ahead and just sort things out. Sine theta over theta, sine 3 theta over 3 theta, 3 over cos theta cos 3 theta. And I told you that we don't have to worry if your cos is at the bottom, because cos 0 is just 1. Actually, I skipped some steps. You should know that this equals to 1, and you should know that this equals to 1, and you should know that this one is 3 over 1, so it's 3. Finish. Alright, move on to number 3. Okay, so this time your sine theta is under power. So whenever you have something very weird as exponent, your first guess is maybe you need to tag y equals to this function here. Then you use tag natural log ln on both sides. Then you make the power flies down, isn't it? But in this case, I see that L'Hopital's rule is an easier approach if you know how to differentiate 3 to the sine theta. Okay, so I will show you now by L'Hopital's, because I only have to differentiate 1 times, then I can already get my answer. Why? Because the derivative of theta is just 1, so I will not get anything crazy at the bottom. Now it would be the limit as theta approach 0 of 3 sine theta. Remember, because this is not base e, this is base 3, so you need to multiply with a ln 3. Then differentiate sine theta, you get a cos theta. Differentiate negative 1, you get a 0. Then like I said, this equals 1. And yeah, you're pretty much done. If you put in 0, you have 3 raised to sine 0 is 0. Ln 3 is a constant. Cos 0 is a 1. So the answer will just be ln 3. Finish. Okay, next we have this. So again, it will be easier to use L'Hopital's. Why? Because you only have to differentiate 1 time. No, I don't know how many times we need to differentiate, but seems like using L'Hopital's is easier than using logarithmic. What's that? I don't know. Yeah, logarithmic manipulation. Okay, so I will just use L'Hopital's rule. And before I check, actually just now I forgot to mention, you have to check whether it is 0 over 0 or infinity over infinity. Like in this case, it is actually 3 to the 0 minus 1 over 0. This is just 1 minus 0 is 0 over 0. Yes, you have the passport. What about this one? This one immediately is 0 over, this is 2 to the 0 is 1 minus 1 is 0. Okay, you have the passport. Okay, so before you use L'Hopital's rule, you always need to check. Okay, then x approach 0 of, okay, this is a product rule if you have learned differentiation, right? And again, this is not base e, so you need to multiply by ln 2 again, plus 2x times 1 over, 2x ln 2 minus 0. And yeah, we can factor out the 2 to the power x, right? And we are left with what? Okay, if we put in 0, the whole thing here will just be 0 here, right? So it is just 1 over ln 2. Finish. Okay, please check if I have made any mistake, because I know I skipped a lot of steps here. Okay, next. Okay, so now we have nth root of something, and whenever you see nth root of something, immediately what comes to your mind should be the table, alright? This table. And root of something. And in this case, it is actually very nice because you know that you can split it into two, which is something like this. Limit or some okay. And to the somehow and some more your this n and n root I can cancel, so it will just be 4 times this one is what? Is 1 from table, isn't it? So it's 4 times 1 by table. Answer is 4. Finish. Okay, very nice. Okay, the next one, it's actually one-sided limits, and we have a secant over 1 plus tangent x. So what happens if we directly put in our pi over 2? And there is a reason why it has to be approached from the left. Okay, so if we put in pi over 2 from the left, secant pi over 2 from the left is actually positive infinity. Okay, right? Let me show you the graph. Secant pi over 2 from the left, it is positive infinity. Then what about, what's that? Tangent pi over 2 from the left, also infinity, isn't it? Also positive infinity, right? Tangent pi over 2 from the left is positive infinity. Okay? So you have a positive infinity over positive infinity. Okay. So you can use L'Hopital's rule. But before we proceed, let me tell you why we need to say whether it is from the left or from the right. Because if we didn't specify, one of them is from, let's say your secant is approached from the left, then you have a positive infinity. Then your tangent, I somehow tell you that, it is from the right. Then what happened? It is actually a negative infinity. This is why the question has to specify whether it is from the left or from the right. But anyway, this happens to be positive infinity over positive infinity. Therefore, you can use L'Hopital's rule. And by the way, in previous lesson we discussed about how we use the hedge approach for one-sided limits, right? And this will not work here because it is like secant and tangent. If you try hedge approach, you will still get the same thing at the end of the day. So we directly use L'Hopital's rule. Okay, L'Hopital's rule. Then if you know how to differentiate this trigonometric function, then it will be good. Secant is actually secant x tangent x. Then 1 plus, no more 1 plus because we differentiate. Differentiate 1 is a 0. Differentiate tangent x is a secant square x. And very nice, this and that can cancel. Wait, should we cancel it? Okay, yeah, I think we should. Okay, let me just do one more, which is this actually sine x over cos x. Then secant x at the bottom, you flip it, becomes cos x over 1, isn't it? So this cos x and cos x can cancel again. So at the end of the day, you have sine pi over 2 from the left. Okay, let me just write. Okay, we can't just write from left from on that one. And you know that the limit when x approach pi over 2 from the left of sine x is equals to 1. Okay, so when you reach these steps, actually you can do the hedge approach. Okay, but actually no need lah, because you know that for pi over 2 from the right or from the left, both of them will get a 1. Okay, so no need lah, you know the answer is 1. And that's it. Okay, then next, number 7. Okay. Okay. So actually, as you can see, it is x to infinity. And how come this one? I think this one don't belong here. I don't think this is a question. It should be the other question. Maybe a typo, because you see this is x, right? This is x, and how come suddenly got n, right? So I think the question should be just like that. Okay, anyway, if you put in infinity, you will have ln infinity. Ln infinity is infinity. Log base 2 of infinity is also infinity. Hence, you can use the L'Hopital's rule. And because why? Because ln is easy to differentiate. Okay, it's not easy. Okay, how should I put it? It's like we know the derivative of ln function and log function. Okay, so I just go ahead and differentiate top, differentiate bottom. I will have 1 over x plus 1, then times 1 actually. Then log base 2, okay, this is 1 over x times, remember, because you are not doing natural log, hence you have to divide by ln that base again. Okay, then just go ahead and flip it, and I think it works now, right? Because well, no, we can't. It is still infinity over infinity. Then just go ahead and differentiate again. Ln 2 is a constant. This is just 1 plus 0. Yeah, so the answer will just be ln 2. Finish. Okay. Next. Oh, we have sine inverse of 5x. Okay. So over x, if you put in that one, nope, it won't work because it is sine inverse. I was thinking about sine 5x over 5x, but it happens to be sine inverse. So they are not the same, okay? So just be a little bit careful. And now what? L'Hopital's, because you know that after you differentiate one time, this will just becomes a 1. So just by L'Hopital's, provided that you know how to differentiate arc sine, okay? It will just be the limit as x approach 0 of, okay, you differentiate arc sine will be 1 over the square root of 1 plus that function square, am I right? 1 plus, is it 5x, is it 25x squared? Not sure. Okay, see, even I can't remember the formula for that. What is the derivatives for arc sine? Oh, it's a minus, okay, sorry, minus 25x squared. Am I right? Then times with the derivatives for inside, which is a 5. Then over a 1. Okay. Then if you put in 0, actually it doesn't matter because this will be 0 anyway, right? So it will just be 5 over 1. So the answer will be 5. Finish. Okay. Next, number 9. Oh, arctangent again. Oh, arctangent, I remember it should be 1 over 1 plus u squared du dx. This one I remember, but I was confused with the sine inverse and sine inverse and sine inverse. Two of them are quite confusing. Okay, anyway, tangent inverse. So we are doing to infinity. So if we put it infinity, remember from the arctangent graph, when we take tangent inverse to infinity, you should have is it 0? Should be a 0. Wait, sorry, not 0. Should be infinity, right? Or pi over 2. Then okay, so we need to make sure that we can use L'Hopital's before we proceed. So let me just check for a while. What's that? Tangent inverse graph. I don't have the tangent inverse graph in this slide, so give me some time. Where is my tangent inverse? Yeah, tangent inverse, if you go to infinity, is going to be pi over 2. Oh, then it will be the pi over 2 divided by infinity. Is it supposed to be tangent or arctangent? Because in that case we can't use L'Hopital's rule. So anyway, just start this and I will come back to this later, alright? Okay, next, number 10, get shine of ln n and n approach infinity. So a simple way of doing this is to use the definition of shine, which is, let's see, okay, e to the ln n minus 1 over e to the ln n. Why did I say this is an easier approach? Because I know that e and ln can cancel out each other, right? So it will be very easy now, which is just 1 minus 1 over n over 2. And this is infinity. Okay, before that, this is 0, this is infinity. So the answer will be infinity. Finish. Okay. Okay, we have 5 more questions. And number 9, I will come to this later. Okay, number 11. Oh. Okay, I think this typo should be n approach infinity here. Okay. So what happens if we put in infinity? You have infinity raised to 1 over infinity, which is 0. And this is again an indeterminate form that we cannot use L'Hopital's rule. So we have no choice but to manipulate this before we use L'Hopital's, right? So whenever you have a power, a very weird power on top, I told you, just introduce another fella, which is y. Be this fella here, 5n 1 over n, so that you can take natural log on both sides and you can bring down the power. So should be 1 over n ln 3 to the n plus 5 to the n. And now what? Now what? L'Hopital's. By L'Hopital's rule. Can you, okay, before that, I forgot to check again. This is actually a quotient of ln 3 to the n plus 5 to the n over n, right? So if you put it in infinity, it will be infinity over infinity. Yes, you have the passport to use L'Hopital's. Okay? So now it will be limit when n approach infinity of ln y. It is equals to, you go and differentiate this, it is 1 over 3 to the n plus 5 to the n. Then you need to multiply with the derivatives inside, which is 3 to the n ln 3 plus 5 to the n ln 5. Then the whole thing over 1. Okay? Then, oh, this is very interesting. This is very interesting. Okay, let me just write it clearer to you. 5n ln 5. 3n plus 5n. Now it is still infinity over infinity, isn't it? So you know that you need to get rid of something, which is either 3 to the n or 5 to the n. Which one should you take? So remember, let me give you some hint here. You look at theorem number 4 in the table. If your absolute value is smaller than of x is smaller than 1, then this value here, the limit will be 0, which means if it is 1 over 2 to infinity, which is actually 1 over 2 to infinity, which is 1 over infinity, you know that this is 0, right? But it is not 0 if it is 2 over 1. Okay, it will just be infinity. Okay, so I told you we need to get rid of something, which means we need to divide both numerator and denominator by the same number. And in this case, should we divide by 5 to the n or 3 to the n? If we divide by 3 to the n, we will have 5n over 3n, which is 5 over 3 is greater than 1. Hence, what we should do is we divide both top and bottom by 1 over 5, divide by 5 over n. And now what? Okay, I'm running out of space, so I'm going to the next page. Alright, So now, okay, let me just copy it here. Ln y equals to, okay, I forgot the limit again. Limit, okay, limit. Okay, now what? I divide by this fella here, so now I have 3 over 5 and ln 3 plus 1 times ln 5, which is ln 5, right? Plus ln 5 over, again, 3 over 5 to the power n plus 1. And this is very nice because I can say this is 0, this is 0. Okay, I don't think you can see it here. Okay, this is 0, this is 0. Means the whole thing here, okay, let me just like, okay. The whole thing here is 0. So the answer will just be ln y equals to ln 5. Hence, y would be e to the ln 5. And e and ln can cancel. Y equals to 5. And that's it. That's the answer. Because your y is this, is the question, isn't it? So I will write limit n approach infinity of the question 3n plus 5n to the 1 over n equals to 5. Finish. Wow, this is a very interesting question. You see, you need to make use of this logarithmic manipulation. You need to use L'Hopital's rule. Not only that, you need to do this kind of manipulation. Not only that, this manipulation is based on your table, how you make use of the formulas in your table. Okay, so this is a very good question. Okay, we shall proceed to the next one. Number 12. Oh, we have tons of that one again, trigonometry. And this time, okay, we can still try the sine theta over theta because we do have an angle here and it is approach 0. But it will be very complicated. For sure, it will be very complicated because we have a lot of functions here, isn't it? So just do it slowly, okay? Limit theta approach 0. The first one, I will just take the theta and I give it to one of this sine, okay? Sine theta. And now I have another sine theta left over. Okay, I will just write 1 over sine theta. And I know that later I will need the theta for this sine theta. Just write it. Okay, next I have cotangent 4 theta. Cotangent is cos over sine. And later I need 4 theta over 4 theta. 4 theta for this fella here. Just prepare everything, just prepare everything. I know it's a little bit of very long, but just prepare everything first. Okay? And wait, let me see. Okay, so cotangent 2 theta. Okay, you see, you know why? Because now I have a problem. You see, this sine theta belongs to this theta. This sine theta, this 4 theta belongs to this sine 4 theta. And this theta belongs to this sine theta. So now, if I go ahead and continue to expand, I will still have this 4 theta and theta at the denominator, which is 0, which can't be in the, denominator, isn't it? So, for the next one, okay, which is this cotangent, I'm not going to assign any more theta to them. You'll know why later, okay? Now you see cotangent square, if you flip it, it is actually sine over cos. And let's write it like this, okay? Sine 2 theta over cos 2 theta times sine 2 theta cos 2 theta. The reason I don't assign any more theta to this fella is because when I multiply 2 of them together, I will have 4 theta square, right? And this 4 theta square can be divided into 2 theta times 2 theta. and I just have to give 1 to each of them, right? Okay, it's a little bit messy here. I'll write it nicer in the next step. Okay, so this is actually very, yeah, it just happened to be like that. So, okay, this is just like this, then theta over sine theta, this is a yellow one. Then 4 theta over sine 4 theta. Okay, this is a yellow one. And now I'm dealing with the blue color one. I hope you can see this. This theta times 4 theta is 4 theta squared. And this 4 theta squared, because I need 2 theta. I need 2 theta in order to make this and this. This is very nice. This is a blue one, just in case you can't visualize it. Okay, so this is the first yellow, blue. And what's left? Okay, so actually the blue color one is this one. So I'm getting rid of this and this. And what else? The cost, right? All the costs. I'm leaving with all. But cost, actually, I told you you don't have to worry because it is just going to be 1. Did I miss out anything? Did I miss out anything? No. Okay, so this will be 1, 1, 1, 1, 1, 1, 1. Finish. This is very nice. Oh, 2 of these question 11 and number 12 are all very nice question. Okay, so we'll proceed with the next one. Okay, we have a weird power, and for this one we can't directly use table. Why? Because in a table, nth root of n, it has to be nth only. It has to be 1 term only, and in this case we have 2 terms inside. So we have no choice but to introduce let y, right? Okay, let y be, okay, I will just write it in exponential form instead of surd form. Ln y would be 1 over n ln n squared plus n. And this happens to be a quotient that is infinity over infinity if we put in limits to infinity. Okay, so we can use L'Hopital's rule. By L'Hopital's rule, the limit as n approach infinity of ln y, limit n approach infinity of this one, you directly differentiate, it will be 1 over n squared plus n times the derivatives of the inside function, which is 2n plus 1. Then over, you differentiate n, you get a 1. Okay, so again, this is not good. Why? Because it is infinity over infinity again, right? Because the power on top is small, the degree on top is smaller than that of the degree of the bottom. So we need to use L'Hopital's rule again. L'Hopital's times 2, okay? L'Hopital's square. Whatever you want to write this. Okay, so L'Hopital's again, we have a 2 on top, 2n plus 1 at the bottom. This time, we can say, if you put it infinity, the whole thing here will be infinity, hence it will be 0, because a very small number over a very big number should be 0. Hence, the limit as n approach infinity of ln y is 0, limit n approach infinity of y is e to the 0, which is 1, and that's it, that's the answer. N approach infinity of n root of n squared plus n is equal to 1, finish. Okay? We are almost done. Number 14. Oh, we have a factorial. So definitely, because we don't know how to differentiate factorial. Okay, we don't know how to differentiate factorial. So we have no choice but we can only use this table. Okay? But the problem is, how do we make it in this form? X to the n over n factorial. X to the n over n factorial, any x will do, right? So I'm just going to split this first, because I know that this two fella is definitely going to give me infinity, right? So the answer is either infinity or 0. Okay, then what's left? Oh, okay, I didn't see this just now. 2 to the negative n means when you flip it on top, it will be 2 to the n over n factorial, and this is very easy because this is just 0 by table. Hence, I don't care what is in front. 0 times infinity is still 0, finish. Very nice. Okay, last one. Okay, another indeterminate form that we can't use L'Hopital's, right? If you put infinity, it will be infinity minus square root of infinity minus infinity again. This indeterminate inside an indeterminate, so definitely we can't directly use L'Hopital's. Okay, so in order to use L'Hopital's, let me repeat again for the last time in this chapter, you need a quotient. You need a quotient, but you don't have a quotient here. So you need to make your own quotient. And whenever you see something like a square root of that, do you have the urge to get rid of that square root or not? Just like what we did in the beginning of the chapter. What we did was, remember, multiply by conjugates. N plus, and now you have your what's that, quotient. I'm not sure if this works, but whenever I see like a square root or something like that, I want to get rid of that, so I just use multiply by conjugate. A square minus b square, and a square minus square and square root cancel. Yeah, we have this at the bottom. Okay, and now what? Okay, let me just write one more step, and so that you can see what I see. N over n plus n square minus n. Can you see that the degree of numerator, the degree is 1, and the degree at denominator, after you open up the square root, it will also be 1. When the degree on top and the degree at the bottom are the same, means your answer should be some constant. Okay, let me write. No constant. Okay, coefficient of the highest power. The coefficient of n on top is 1. Definitely 1. I hope you don't make this mistake. You don't tell me it's 0, okay? What about at the bottom? You need to be a little bit careful. After you open up this, you already have one n here. After you open up, you have another n. So the coefficient of n is actually 2. Hence, the limit would be 1 over 2. Okay? Yeah, so this is very nice, and this is all for today. Okay, so you have learned how to use L'Hopital's rule, and also how to make use of the table when you are evaluating limits. Alright, so this is actually like the introduction to L'Hopital's rule. We will actually further this together with the indeterminate forms in more advanced chapter. Alright, so that's all for today. See you guys in the next class.